Hello. In this video, we're going to analyze how to estimate the filter coefficients adaptively, which means that we want to compute the filter estimate just at the same time that we are observing the filter outputs a long time. So, well, let's review what we have seen up to now. We have assumed that a signal U of n is the input to a linear time invariant system S, whose coefficients we don't know, and the output is affected by no, so we only observe X, which is the convolution of S and U, plus some noise. We have reformulated the estimation problem using vector notation, so we have transformed these signal equations into a vectorial equation using a vector S containing the filter coefficients, a vector x containing the output signal, a vector u of n, which is the state vector containing all the samples from u that are relevant to compute the output at time n, and a matrix capital U, which is just a matrix that concatenates all state vectors. So we have analyzed the problem from an estimation theory perspective, and we have actually solved it by finding the optimal minimum mean square error estimates of the filter coefficients, which is given by these formulas here in green. We have seen that the posterior distribution of S given X is a Gaussian distribution, and both the mean and the variance depend on some matrix which we have called P, which is equal, which is given by this expression here. The minimum mean square error estimate will be equal to the map and the MAD estimates, and is given by P times U times X. Well, this coincidence is caused by the Gaussianity of the posterior distribution, which is also a consequence of the Gaussianity of the noise. So this solution has a great advantage, computational advantage, because we have an explicit formula for the filter coefficients, and this is good. But there are some applications where we may be interested in computing the filter estimates at the same time that we are observing the signal output. So if we have observed the signal up to time n, we need to compute an estimate, and as time progresses, we need to update our estimate. Well, we can't just apply these formulas every time, but this has two main disadvantages. The first one is that the signal output x is a vector whose dimension grows with the number of samples, and also the matrix U grows with the sample size. So, well, this could state some memory problems. And another disadvantage is that in order to update the estimate, we have to compute again these formulas, and this include the inversion and a matrix inversion, which is computationally expensive in general because it takes about a complexity about the square of the number of filter coefficients. So the computation of this is proportional to m cube. To the cube of the number of filter coefficients. And well, in this real-time applications, this is not feasible. So we would like to have some way to update the filter coefficients iteratively without needing to store the whole signal, and also trying to avoid the computational complexity of the matrix inversion. And it turns out that we can do that, and we will see how. Okay. To do that, we will assume that, well, we will call this vector capital U, and UN minus 1 is the matrix capital U will have an index n minus 1, indicating the number of columns, the number of state vectors we have. The minimum mean square error estimate will be equal to the map and the map estimation is given by P times U times X. Well, this coincidence is caused by the Gaussianity of the posterior distribution, which is also a consequence of the Gaussianity of the noise. So this solution has a great advantage, computational advantage, because we have an explicit formula for the filter coefficients, and this is good. There are many applications where we can be interested in estimating the filter coefficients at the same time that we are observing the signal outputs. So and these equations are useful to compute estimate for any number of samples, so we can just apply these equations iteratively every time we have observed new output samples. However, this has some disadvantages, memory and computational disadvantages. From the memory point of view, this is problematic because we need to store the whole signal and the whole matrix capital U at every iteration. And also we need to compute a matrix inversion at every iteration. The computational cost of inverting a matrix with dimension capital M is proportional to the cube of the matrix dimension. So we would like to have an algorithm that could allow us to compute the filter estimates iteratively without needing to estimate to keep the whole signal in memory and without computing matrix capital P, the inversion of the matrix. So, well, actually it happens that we can do that. So, and we will see how to do it. First of all, we will call P capital U n minus 1 to the matrix which has all the state vectors up to time n minus 1, and we will call Pn, we will call Pn P sub n, and to the inversion when we use the capital U at time n. And we will define also a vector Rn, which is the product of Un times x. Okay. So we will see that we can compute Pn, Rn, and also the filter estimates iteratively without needing to compute any matrix inversion. So we will try to find recursive formulas for Pn and Rn. Well, the second one is the easiest one. We can say that Rn plus 1 is equal to Un plus 1 times x. I will make the number of samples in x also explicit. Let's call this the vector containing all samples up to time n minus 1 will be x sub n minus 1. So at time n we will need Un times xn. So at time n plus 1 we need Un plus 1 xn plus 1, and this is equal to the matrix with columns u of 0 up to u of n plus 1, u of n, and u of n plus 1 times x n plus 1, which is the vector containing x0 up to xn, xn plus 1. Okay, and now we can compute this product as block product computation. So this is equal to the product of this block here times this block here, and this is exactly un times xn, and we have to add the last term, which is un plus 1 times xn plus 1. Okay, and now we can see that this term here is exactly the same term here but at time n, so this is Rn plus u n plus 1 x n plus 1. So we have a first equation that could allow us to compute R iteratively. Okay. Well, the iterative computation of capital Pn is a bit more complicated, but we can just give at least some idea about how it works. Pn plus 1 is equal to un plus 1, un plus 1 transpose plus sigma epsilon square divided by sigma s square times the identity matrix to the minus 1. And we can make the same decomposition that we have done here. Un plus 1 is equal to these terms here, which are un and u of n plus 1. So the matrix un plus 1 can be expressed as a block matrix with two blocks. The first one is un, and the last one is un plus 1. It has to be multiplied by itself. Un plus 1 transpose and plus sigma epsilon square times sigma s square times the identity matrix to the minus 1. And this can be written as un times un transpose, which is the first term in the product here, plus sigma epsilon square divided by sigma s square times the identity matrix, which is the last term here, and plus u at time n plus 1 times u at time m plus 1 transpose. And we must compute the inverse of this. Okay. By looking at this expression, we can see that this term here, the sum of the first two terms, is just the same than we have here. We miss the minus 1 here, the inversion, so all this term here is just Pn to the minus 1. So we can write this as Pn to the minus 1 plus u n plus 1 times u n plus 1 transpose. And we have to compute the inversion of that. of this. Well, how can we compute this inversion? Well, actually, we can here apply a property of matrix, which is usually called the matrix inversion lemma. Well, I will skip the details, but applying the matrix inversion lemma, it can be shown that this inversion is actually equivalent to Pn plus or minus Pn Pn u n plus 1 u n plus 1 transpose Pn divided by 1 plus u n plus 1 transpose Pn u n plus 1. Okay. And there we have the second recursive equation we need. We can compute p at time n plus 1 as a function of p at time n using this expression. Well, in verifying this equality, the last equality here is not actually complicated. Since this function, this matrix is the inverse of this one, we can just multiply both to verify that the product of both is the identity matrix. So this is the easiest way to test that the matrix inversion lemma works here. Okay, so we could do that. It's not difficult, but I will skip the details. So we have two recursive equations, and the important thing here is that we have no longer to compute the inverse of a matrix, and also know that in these final equations we don't need nor x, neither x nor the matrix capital U. So we have removed all memory and computational problems we had with the original formulas. So using these equations, this would be, let's say, equation 1 and equation 2. Well, once we have P and R, remind that the filter coefficients can be estimated as P times U times X, and this is just P times U times X, which is R. So the third step would be to compute the estimate as P n plus 1 times R n plus 1. Okay, and this would be the third equation. So with all this, we can see that we can compute the filter coefficients iteratively without memory problems and without estimating the filter coefficients. Besides of this, well, the computational cost here is just proportional to basically to m squared, to the dimension, the number of filter coefficients, the dimension of vector S to the square, okay? Because we have to compute here the products of matrices times vectors, and well, it's easy to see that this computation involves the square of m. We can even go a bit farther and estimate the filters with even less computational cost using what is called an algorithm which is called the least mean squares. Well, I forgot to say that the previous algorithm has name The algorithm composed by these three steps has a name. This is the recursive least squares algorithm, or RLS. And now we will see that we can also estimate the filter coefficients using an algorithm which is usually called the least mean squares algorithm. And the idea of these algorithms, this is an algorithm useful to compute the maximum likelihood estimate SML. Okay. Well, using the expression for the likelihood, well, we can see that the maximum likelihood estimate is the value maximizing with respect to S, the likelihood function. And actually, we have computed the form of the likelihood function in a previous part of the analysis. Just here, we have seen that the maximum likelihood estimate is given by the minimization of this expression here. So we know that the maximum likelihood estimate is given by the value of S minimizing the norm of X minus U transpose S to the square. Okay. So we can express now X minus U transpose S to the square as a sum. Well, this is exactly the sum. Well, we can compute this component-wise. So this is the sum of the square difference of the components of X and U transpose S. So this is exactly the same as the sum of Xn minus U of n transpose S square. Okay. And which is a function which depends on the coefficients S. Okay. So, and to estimate the parameters, the vector of coefficients, we can apply the gradient descent method. Okay. The idea of gradient descent method is that we can compute S iteratively. Okay. As the previous value minus some parameter mu, that is a free parameter of the algorithm, times the gradient of the function that we want to minimize with respect to S. Okay. So this is a gradient descent strategy. Basically, the idea of gradient descent methods is that if we want to minimize a function which depends on S, in this case the norm of X minus U transpose S, We can start from an arbitrary position, an arbitrary value of S0, and modify it iteratively just by modifying our estimate in the direction where the slope of the function that we want to minimize decreases or decreases faster. And the direction of the fastest decrease is just the gradient of the function. So, well, this leads to the gradient descent algorithm. The estimation at time at n plus 1 is equal to the estimation at n minus mu times the gradient. Okay? So applying the gradient over this formula, we can say that this is equal to Sn. I will write here an accent to indicate that this is an estimator. This is Sn plus mu plus the sum from n equal to 0 to up to n of x of n minus u of n transpose s of n times u of n. Okay? So this is the gradient descent algorithm. And well, the computational cost of this function is proportional to the number of samples. So in order to have an algorithm whose complexity doesn't grow with the sample size, we can apply the stochastic version of this, which is called the stochastic gradient descent method. Okay, which basically says that instead of using the whole signal at every time, we can just update the filter coefficients using the most recent observation. Okay? And the result this is cap vector u, and the result is this algorithm here. That we call LMS, or least mean squares. Okay. Well, the stochastic gradient is the generic strategy for minimization based on gradients, consisting on using only the most recent value. And when we apply to this strategy to estimate the filter coefficients, it is usually called LMS, or least mean squares. So, these are two names for essentially the same thing here. Okay. Well, this is capital M because we are using the vector at time n. Well, the computational complexity of this algorithm is just linear with the dimension of vector u. Is linear with m. It's proportional to the number of filter coefficients. And so this is the main advantages of these algorithms. Actually, well, this algorithm only approximates the solution because we are using just at every time we are using just a single step of an iterative algorithm. So in general, well, basically, while the recursively square is an optimal algorithm, computes exactly the minimum mean square error estimates, the stochastic gradient descent, or the LMS, only approximates the maximum likelihood estimate at every time. Okay.